I just want to look at a particular instant. I pulled out some data from the clip because it gives the speed really nicely. It told us that at t equal 21 seconds that the velocity was 697 kilometers per hour. Um, First of all, I want to know what distance has he fallen at that point, and then I want to calculate what his velocity should have been. We'll see if there's any difference in what the measured velocity is and what it should have been, because we can calculate it pretty simply from our kinematics equations. First of all, we need to convert this to meters per second. You will have to do some conversions on the exam on Friday, so make sure that you're up on that. I will provide you the conversion factors for the British system between systems, but not within the metric system. So for example, I will not provide you kilometers. That comes out to be 194 meters per second. Every second, going 200 meters. Every second. I think I was zooming. Right, 600, almost 200 meters per second. And now I want to know what is his, this is the measured. Let's calculate what that velocity should be. So I can say that v is equal to v naught plus at. And if I do that, what's his initial speed? We'll say it's 0, yeah, sure. So it's equal to 0 plus a negative 10 meters per second squared. Oh, and this occurred at 21 seconds. And so that's equal to 210 meters per second. So we see a difference in these two values, right? This was as measured, and this is our theoretical value that we calculate just based on the time that he's in air and the acceleration. Why are these two different? There are a couple of reasons. Why are they different? Why is this one, the measured, actually slower? Okay, friction is one of them, maybe. Although with air resistance, there's not a whole lot of atmosphere that high up, so I think it's probably going to be a little bit small, the effect. But air resistance could be one of those. What's a second thing that we've assumed here that may or may not be true? That's probably not true, in fact. Okay, that could have a small effect, and in fact, the gravitational force will be slightly less up at a higher height. So yeah, that's one thing, that the gravitational acceleration here could actually be less than 10, and it is a little bit less than 10, but probably not enough to make such a big difference. So maybe a third thing then. What's a third thing? All right, well, when he jumps off, what is he doing? He's in a balloon, right? What do balloons do typically? They go up, right? But we've assumed here that our initial velocity is 0, and so that's probably not entirely true. So several things. One, air resistance, as Ainsley said, that's going to slow them down. We won't deal with air resistance in this chapter. We'll see it a little bit in chapter 4. The second thing is the acceleration due to gravity is actually going to be less than 10 meters per second squared. We'll talk about that again. Oh, gosh, when do we get to that? After chapter 4. That the acceleration due to gravity as you go away from the Earth decreases. And so that's probably a fact as well. And then the third thing is that because the balloon is actually going up, the initial velocity is probably greater than 0 meters per second. And all of those would cause your calculated value to be bigger than your actual measured value. All right. Let's also calculate the distance that he traveled. So if I want to find the distance, I just say y is equal to v naught t plus 1/2 at squared. Remember, you'll need to know these two equations. We derived them. They're pretty easy to derive, but you'll just need to know them. Put them on a post-it note, paste it to your door or your wall, whatever, so you can see it. We can calculate this. It's going to be pretty simple, just 1/2 a t squared, 1/2 of negative 10 times 21 seconds squared, and that's equal to 2,200 meters. All right, so that's sort of basically how those equations work and a way to use them. We're going to work through some sample problems. I think now that we will, can I go down from here, y'all? I sent out some supplemental problems. Let me see what's next. Yeah, we'll hold off on this. And let's do some of those supplemental problems. really, your test questions will look something like this. You have homework questions that'll help prepare you for the exam as well, and then looking back at the old exams will help you as well. So this week, as you're preparing for the exam tonight and Tuesday night and Wednesday night and Thursday night, uh, please work through some of these kinematics equations. Right? So let's look at this. This was in those supplemental problems. These aren't in your book, unfortunately. I sent them out last week. Did y'all get those? Sent out. So consider a gray squirrel falling out of a tree to the ground. If we ignore air resistance in this case, only for the sake of this problem, determine the squirrel's velocity just before hitting the ground, assuming it fell from a height of 3 meters. And then there's part B as well. So let's see. The first thing whenever you encounter these problems, you just want to write down everything that you know. Right? And sometimes things are stated explicitly, and sometimes they're not stated explicitly. So let's just sort of go through. I have a gray squirrel falling out of a tree to the ground. What can I preen out of that statement? A couple different things that I can pull out of that statement. They're not stated explicitly, but I can assume them to be true. Okay, I can find the acceleration. I'll go and write it down. Acceleration is minus 10 meters per second squared. And what's the second thing that I can find? The initial velocity is what, Cody? Is 0. So I have this squirrel that's falling out, and he has an initial velocity equal to 0. So I always like to just make a little column of all the things that I know in a problem, and then I can start looking at my equations and figure out how to solve those equations to get what I'm being asked for. Okay, if we ignore air resistance, that means that the acceleration will be equal to negative 10, not less, not more. Determine the squirrel's velocity before hitting the ground. So I want to know what is v. That's what I'm being asked for. Okay, I can draw a little picture over here if that helps you. Here's my squirrel. He's falling a distance. I know v naught equals 0. I want to know the velocity here. And then I also know that he falls a height equal to 3 meters. Okay, you need to be very careful here in how we assign the initial position and the coordinate system that we use. I recommend that you do it this way, although there are different ways you can do this. I recommend that you always say that the initial position, y naught, is equal to 0 meters. Just because typically we don't, that's just typically what our initial position is. But if y naught is equal to 10 meters, then what is your final position going to be? It's going to be negative 3 meters. So it's as if you're drawing your coordinate system right here. So this is the positive y, and this is negative y. So if y naught is 0 meters, which you know, why not, right? Then did I already use that little pun in here? No, sorry, I have several classes, and sometimes I cross over my things. So here, my y is equal to negative 3 meters. So I can go ahead and write that my y final, my final position, is negative 3 meters. All right. I don't know the time either. Just looking at part A, I don't know the time. So now let's write our equations. I think that's all that we know, right? And that we don't know, that we're being asked for. We're particularly looking for this value. I'm going to say V equals V naught plus AT, and then Y equals V naught T plus 1/2 AT squared. I want to look at each equation and see what I know and what I don't know. Here, I don't know V, but I also don't know T. So can I solve this equation? No. Here, let's see. I don't know T, but I know Y. This is 0. Can I solve this equation? I can. And what will I solve it for? T. So it looks like for this problem, what we're going to need to do is to solve the distance equation, the displacement equation, or the position function for T, and then plug that back in to find our V. It's going to be different for every problem. Sometimes you might actually have to substitute one equation into another. I think we have to do that in part B of this problem. And likely, you're probably going to have to do that on the test. But in this case, it's a pretty simple problem. I'm just solving this for t and plugging it in there. It's a pretty easy solution because v naught is 0, so that whole term goes away because 0 times any number is 0. And let's see, why don't y'all just take a minute and start solving that, doing the algebra, solving that first one for t, or rather this one for t, and then plugging in to find v. So take just a minute. Anybody have t yet? Claire, you have it? Point 77. Let's see, yeah, 0.77. So I say y is -3 equals -5, that's half of 10 times t squared, and t is 0.77, the square root of 0.6, which is 0.77 seconds. And then I can find my v here. What is v? What is it going to be? Right, it's just going to be 10 times 0.77. So v is equal to a times t, because this is 0. That's -10 times 0.77. That's -7.7 meters per second. All right. Now, for the next problem, it's a little more complicated. Now we're going to have a different situation. We're going to have the squirrel. I'm going to sort of blow up this area. I have the squirrel. He's right here. And he puts his legs down to stop himself. All right, so the squirrel, just as he's hitting the ground, he falls a certain distance. He puts his little legs out on the ground, and his legs do like this, right? You ever seen a squirrel jump on the ground from like really high? He bends his legs to absorb or to decelerate in that amount of time. I know that this distance is 2 centimeters, and I know that the acceleration, or rather I don't know the acceleration in this case. Um, what are some other things that I know for this scenario? Forgetting about the first part of the problem, now we're looking at a completely separate problem. What are some things that I know about this? Like what's his initial velocity? What's his final velocity? How much time is he in motion? And what's the acceleration? So what are some things that I know about this scenario? Okay, I do know how far he's fallen, but at this point, that's not really relevant. Beans, what were you saying? Right, I know his final velocity, so let's write that down. It's 0. No, actually quite a bit. So his final velocity is equal to 0 meters per second because he comes to rest. What else do I know, yo? Ainsley, were you talking about the 2 centimeters or the 7.7 or the 3 meters? Okay, what is his initial velocity? Do I know what is the squirrel's initial velocity? You're barking up the right tree. That's right, it's -7.7. That's what you were thinking, huh? Yeah, so this velocity, which was his final velocity before, is now going to be his initial velocity here. So that velocity that we found is now going to be his initial velocity. So my v naught is going to be -7.7 meters per second. What else do I know? I'm sorry, what now? I don't know the time, actually, but we'll list it there as being an unknown. What else? I don't know acceleration, likewise. There is something else that I do know. the displacement, right. So his final position is equal to 2 centimeters. But remember, we need to make sure that our coordinate systems are set up properly. So this is our initial position of 0. His final position is going to be negative 2 centimeters. I want to go ahead and convert that to meters. You'll need to be pretty good at converting centimeters to meters. 2 centimeters is how many meters? 200ths, right. There are 100 centimeters in a meter. 2 centimeters is 200ths of a meter. So I'm just going to move that decimal place over one place, two places. So 2 centimeters is just 0.02 meters. We often use centimeters, so it's important. Or nice to be able to do that quickly. So it's 0.02 meters. Now let's write those equations. V equals V naught plus AT Y. I'm going to encounter a problem here when I look at these equations. Somebody tell me what my issue is. I don't know acceleration, and or nor do I know time. And both of those, acceleration and time, are in both equations. So I have two unknowns in two equations. Right? I know everything else, right? I know V, and I know V naught, and I know Y, but I don't know acceleration and time. Anytime you have an equation, and listen, very likely on the exam that you'll have to solve a system of equations like this. I don't even say you shall have a question where you have to solve a system of equations. Uh, just make sure that you sort of do it very orderly, sort of set aside space for each equation and take plenty of space on the paper to do this. You want to look at what you're looking for. So in this problem, I was looking for the acceleration. So what I want to do is take one of the equations and express one of the variables in terms of the acceleration. Yeah, so in this case, I'm going to take this first equation. You can do this different ways, but I'm going to take this first equation, and I'm going to express t in terms of a. Actually, let's clean it up just a little bit, because I know this is equal to 0. So I can say 0 is equal to v naught plus at. And then I'm going to say that t is equal to negative v naught over a. T is negative v naught over a. I'm going to take this, and I'm going to substitute it here, and I'm going to substitute it here. And then I can solve that equation for v naught. So I say y equals v naught times negative v naught over a plus 1/2 of a v naught squared over a squared. All right, I can get rid of, simplify this a little bit. At some point you might want to put numbers in. It sort of depends on what you like. But I can get rid of that a and say this is negative v naught squared over a plus v naught squared over 2a. And that's equal to y. Depending on how you want to do this, like I said, you can put in numbers or not. I'll go and put in numbers here because I know what v naught is. It's negative 7.7. Actually, to make the math easier, guys, I'm just going to make it 8. So I'm going to say that v naught is equal to negative 8, just to make the math a little easier. So this is going to be negative 64 over a plus 64 over 2, that's 32 over a is equal to y. I can add those two because they have a common denominator, and then I just solve for a. Negative 32 over y, negative 32 over negative 0.02. And that's equal to 1,600 meters per second squared. All right, there are different ways to solve a system of equations. If you haven't done this in a while, just make sure you go through. you shall have, I'll give you two equations, you'll have two unknowns, and you'll have to solve them in this way. Uh, you might also have one like part A of this problem, where you have to solve the first part, which doesn't really answer the question, but you can use that information for the second part, like the part A of this question. If I could do this on the test, listen, I get partial credit on the test, so if you show me all your steps and your steps are correct, but in the end you still get the wrong answer, I'll just mark off a couple points. If it's really just a calculation error, as long as you follow the appropriate steps. So make sure that you always show your work. It's really easy for me to grade if I go along and I see no work and then I see the wrong answer because I just count off everything. But if I see a lot of steps that are correct, then I'll try to give you as much credit as I can. Is that clear what I mean by that? It's better for you to show your work. It's better for you just sort of the thought process to go through the steps, but it's better for you to do your work just for grading processes too, grading reasons. You okay with this problem? Yeah, Shane? Right here, because right here I have a negative here, and then I have a negative 8 and another negative 8 here. So negative 8 times negative 8 is 64. But then I had another negative, this negative, which carries on into it. Does that answer your question? You follow? This number, this variable represents a negative number. So I have negative, negative, and negative. And that comes out as a negative. That's a good question. Sorry, I was a little sloppy with that. Okay? Y'all good? Y'all can do this, right? Like if I gave you this question right now, or not this one, but one like it where you have to solve a system, reading the question, picking out the variables, knowing what is what. I find that drawing a picture really helps, and then solving the system of equations. Okie dokie. So far I've already told you two things that will definitely be on the test. You're going to have a function. I'll give you a function for probably the position, and then you have to calculate a variety of things. You have to calculate the velocity function. You have to find the velocity at a particular time. You might have to calculate the distance traveled in a certain period of time. That would be where you take the integral of the velocity function. So you need to know how to do those derivatives and integrals right now. If you aren't up to speed on that, then you need to get up to speed or come see me, I can help you. And then also you'll have a kinematics question, one similar to this. You might have two kinematics questions, one that's involves solving a system of equations, and then maybe one that's a little simpler. Okay? All right. So that's 2 out of probably 4 for your response, which are going to count for most of your test. All right, let's see. Let's back to your notes. I'm sorry that those aren't in your workbook um, this semester. Let's see, I want to show you a little clip. All right, so what in that clip was actually correct about motion? About the motion that what is correct and what he's, Sydney? Okay, he goes up and comes down. What else? What did he do? Right, so he stops, and it's actually really like it's overemphasized that he stops for a really long time. But it is true that when you have something that goes up, it stops before it comes back down again. All right, so what is it about it that's incorrect? And this is pretty common in cartoons. Exactly right, Cody. So that the motion in that clip was not symmetrical. It takes a lot longer to go up than it does to come down, and that's obviously not true. That's not what happens physically. Let's see, we're not going to worry about this 9.8 stuff here, but I do want you to just recognize that there were a couple things that one goes up and comes down, that the velocity at the top was equal to 0, and then also that the time to go up should equal the time to go down, that it should be symmetrical in that way. Let's do some clicker questions. We didn't finish them, did we? Might tell me where we left off? Claire, do you know? Or did we finish them for chapter 2? These. Oh, we did finish them. Okay, great. All right, well, let's work these other two free fall problems. We'll watch this clip from Big Buck Bunny. You ever seen Big Buck Bunny? It's a cartoon, but it's kind of an adult cartoon. It's not really appropriate for kids. But it was part of an open movie project, the Peach Open Movie Project, where they were basically trying to advertise their open source software, this animation software. But it's about a rabbit, a big bunny, and he's kind of naive, and these kids are picking on him. This like flying squirrel and like a hedgehog or something, and then in the end, he sort of stands up for himself, and he I don't know, exacts this revenge on the character. So in this, we're gonna see a couple of instances of free fall. I want you to note the instances of free fall, and then also think about how they're represented differently, because in the clip, the two instances of free fall are represented in different ways. Okay, there were two instances of free fall. What were they? What was the first thing that fell? The what now? Yeah, it's a peach, actually. I mean, I know peach trees are about this tall, but there's a bunch of Swedes that made this. They don't know what a peach tree is. But anyway, it's supposed to be a peach, but it looks like an apple. Uh, yeah, so the peach that fell, and then what was the second thing? The squirrel, right. And they're represented differently in the clip. Did y'all catch how they were shown differently? How was it? When the peach fell, how was it shown? It was in slow motion, right? So we don't have any time information about that, but for the squirrel, it was not, presumably in slow motion. So we can determine sort of how long it took just from looking at the slide. So from that, I we can make some assumptions. Let's look at the peach first. So here's our tree. We have this apple or peach or whatever, and it falls down. All right. We don't know the time that it falls. Um, we can estimate the distance. So we know that y naught is equal to 0, and we can estimate the distance. It looked to me to be a pretty tall tree. I thought maybe 50 to 60 feet. Maybe you'd say a little bit smaller than that. But I'm going to say that the final position then is going to be about 50 or 60 feet. That's about 20 meters. All right. Is this going to be positive or negative? Negative, right. So remember, since my y naught is 0, that means that the final position is going to be negative 20. All right, so y naught is 0, y is negative 20. My v naught is 0, as is often the case, but not necessarily, like in the squirrel problem we had before. And what else do I know here? I know my acceleration. It's not stated, but it's always implied. And I don't know what my final velocity is. And that's what I want to determine. What is the final velocity here? And in the course of that, I also need to find out what is the time. So I can write my equations. Y equals v naught t plus 1/2 at squared, and then v equals v naught plus at. Notice in this second equation, I have two unknowns. I have the final velocity and the time. Both of those are unknowns. I want to know the final velocity, but I can't solve this, so I need to go back to my first equation. I know y, I know v naught is 0, so this whole term goes away. And I know the acceleration. By the way, I'll never have you solve the quadratic. I think I told y'all this, did I not? On a test, I'll never have you solve the quadratic. So anytime you have to solve this equation for t, you should always see that this term will go to 0, just because students often get the quadratic wrong. So you have to do it in lab, but not in here. All right, so I'm going to solve this equation first, noting that that term goes away. I can put in my values here, negative 20 equals 1/2 of negative 10 t squared. That's the square root of 4. So t is 2 seconds. And then I can take this and plug it in there. And I get my final velocity is 0 plus negative 10 times 2, which is 20 meters per second. Or and negative 20 meters per second. All right. So again, stepping through this, you have to write down everything that you know, everything that you want to know. Write out your two equations. When you get your tests, you can write them on your form. You'll have a form on the front of your exam. You can write them there and just use those for reference. But please just memorize them. And then you can solve for your final velocity. That's pretty easy, right? You probably have an exam question like that. Hopefully that is just a gimme question that you get that without much effort. Okay, now we have a second instance of free fall, and that's the squirrel. We're going to assume no air resistance. I know that might not be the case, but we'll assume that there is no air resistance. In this case, we have the time, and I just pulled it off the clip. It was about 4 seconds. So t for this was 4 seconds. Again, the initial velocity is 0. The acceleration is minus 10. The final velocity, I don't know. And I don't know the distance that he fell either. But I want to find it. Anytime you have the time, the problem is going to be pretty simple. Because, well, this one will be pretty straightforward, you'll see. I do want you to recognize here that the time, 4 seconds, is twice that of the peach. Where the peach was just 2 seconds, and this one is twice that time. So let's find the velocity first. It's going to be 0 minus 10 times 4. It's 40 meters per second. How does that speed compare with the speed of the peach? How much more is it by a factor of what? It's double, right. So the time is doubled, and so the velocity is doubled. That's because I have this linear relationship between v and t, that the velocity is directly proportional to the time, and so I have the same acceleration for both. I have the same initial velocity for both. If I double the time, I double the velocity. It's a linear relationship. Sydney? It would be negative. Thank you. So the velocity is negative 40, and then note here that this is twice the peaches because of this linear relationship between v and t. I can also find the distance. Say y equals v naught t, 1/2 at squared. This goes to 0. Can you look at the distance that the peach fell and just tell me right off the bat how far it's going to be without calculating it? How far did the peach fall? 20 meters, right. So how far is this going to fall? It goes twice the time, so it's going to fall how far? What's that? 40? It's going to quadruple. It's going to be 80. Because here I have a quadratic relationship between y and t squared. Y here is proportional to t squared. So if t doubles, y will quadruple times 4. So my y then will be 4 times 20 will be 80 meters. And we can see that if we put in the numbers here. It's 1/2 of negative 10 times t squared. What was t? 4 squared. That's 5 times 16, 50, 80. That's 80. Right. So when I double my time, it quadruples the distance because of this quadratic relationship. We saw that in some of the concept test questions, the clicker questions, and you'll need to be up on that, just sort of knowing how these variables change with the with the different relationships, the linear and the quadratic relationships. Alrighty, let's do another free fall. Very likely have one similar to this. We haven't done one exactly like this yet. I think it's on the next page. Yeah. Probably this morning we'll just look at these first three, and then we'll finish up with D, E, and F. All right, so here I throw an object up, and let's just, as I said, just consider the first three, A, B, and C, where it comes up and then it comes back down. And then on Wednesday, we'll come back and get the latter part. So I have this, I throw it up, it goes to the top, it stops, and it comes back down. And so I want to know what is the time required to reach the maximum height, what is the maximum height at this point, and then what is the time required to return to the guy that throws this rock upwards. He throws it up, it comes down, and it returns back to him. All right, so I want to know the time required to reach the maximum flight. I know that the velocity at the top is equal to 0. I know that my acceleration is minus 10 meters per second squared. And I know that the initial velocity is 20 meters per second. And then I want to know how much time does it take. What was the first? Yeah, what is the time required to reach the maximum height? I'm going to call that T-top. That's like what we were doing before. Now go ahead and try to solve for T-top. Find out what is T-top. Remember we had those two kinematics equations. I showed you how we could solve for this earlier. You could see a question like this on the test. I would consider this sort of a simpler question. Uh, what is T-top? I'm going to redraw the picture over here. You might have the time required to go up? 2 seconds, right. So I just say V equals V naught plus AT. V is 0 equals to 20 plus negative 10 times T. 20 plus negative 20 is 0, so T is equal to 2 seconds. So that is the time required to reach the top. The next part of this problem asked what is the maximum height. Remember, if ever I want to find a position, I have that position function. So I'm going to say y equals v naught t plus 1/2 a t squared. I know that this thing takes 2 seconds to go up, 4 seconds to return back. And so I can just plug in the correct time there to find the y at the top. Yes, Sydney, I'm sorry. What's up? For this one right here, where I take the 20 over to the left-hand side, I subtract 20 from both sides, so I get negative 20 equals negative 10t, and then I divide both sides by negative 10, and I get t equals 2. Got me? All right, so what time am I going to use here to find the y position at the top? 2 or 4 seconds? I'm going to use 2. That's right, Lazarus. So I have v naught times 2 plus 1/2 of negative 10 times 2 squared. So v naught is 20. That's my initial speed times 2 seconds plus 1/2 of a, which is negative 10, times 2 seconds squared. That's 40 minus 5 times 4. That's 20 meters. So that is how high it goes up. This is equal to 20 meters. How high, when he throws this thing up, it goes up 20 meters, giving it an initial speed of 20 meters per second. Notice here, we talked about this before, but if I put in instead 4 seconds, what am I going to get for the y position? Where is that thing at 4 seconds? Where is it? It's going to be at 0. So, and that'll flesh out in your calculation. But I know that it returns to that t equals 0 at 4 seconds. And let's see, was that all the questions? Yeah, what is the time required to reach maximum height? That was t equal 2 seconds. The maximum height we found was 20 meters. And then the time required to return is just going to be 4 seconds. That's just twice the t top, which is going to be 4 seconds. All right, y'all have a great day. Um, we'll do some more kinematics next time and maybe move a little bit into vectors, but that won't be on the exam. So right now you're just focusing on chapters 1 and 2. Please do the homework before next time, okay? If you wait till Thursday, it's going to be a bit of a shock to you.